Welcome. In this episode, we're going to be talking about the integrating factor. The integrating factor is a technique. We want to find a function that we can multiply to both sides of this equation, which will help us to solve this ODE. So this method is applicable when we have a first-order linear equation, essentially something of this form. So the integrating factor is going to be a function, and it's going to be e to the antiderivative of whatever we have here, so p of x. So how is this helpful? So first of all, what happens if we take the derivative of this? Well, chain rule tells us that we get this times the derivative of the inside function, which is p of x. In other words, what you could do is you could write the derivative as r of x times p of x. So now that we know this information, we can go ahead and multiply this, the r of x, to both sides. So let's do that. So here we have r of x, here we have r of x, and here we have r of x. Now notice this here in the box. This here is exactly the derivative of r. So why not go ahead and actually, let's go ahead and erase that, and instead what we do is we write the derivative of x, of r. So now on the left, what do we have here? This looks familiar. This is product rule, the derivative of the first function times the other one, and then the derivative of the other function times the remaining function. So that means that on the left here, what we could do is instead of writing all of this, we could just do r of x and y, and we take the derivative with respect to x. So then, if we want to go ahead and solve for y, we can integrate both sides. So let's go ahead and do that without changing too much here. Well, let's move this to the right, and we can go ahead and integrate both sides. Integrate dx, integrate dx. Now, what we could do here when we're integrating this, we know the antiderivative, and essentially it's this. Now we can go ahead and solve for y. And doing this, what we're going to be getting is this right here. And that's how we solve for y. So what does this actually look practically? Let's go ahead and do an example and actually use this method. So in this method, in this equation, I want you to notice here that we have a first order linear equation. So it's of that form. This here is our p of x, and everything else on the right is our f of x. So sometimes you will have a function of x here. You can always divide it over and get rid of it, but we don't in this case. So our r of x is going to be e to the antiderivative of 3x squared dx, and that's going to be e to the x to the 3. Now, some of you guys might be tempted to put a constant here, and you wouldn't be wrong in doing that, but we don't care about which constant. We want a particular solution. Why not let your constant be 0? So now let's go ahead and multiply this over to the top. So if we do that, what we're going to be getting is this. We're going to go ahead and multiply it over. So we have r of x times y prime plus 3x squared r of x times y is equal, and sine of x, and when you multiply r of x to the right here, Notice that these two cancel, so it's gone. Now on the left here, remember that the derivative of r is exactly this right here. So then we can reduce this as the derivative of r of x times y. So this is what I mean. You multiply r and y, and you take its derivative, and this is what you get. You then integrate both sides to get r of x times y, and the antiderivative of sine of x is going to be negative cosine of x plus some constant. So now we can solve for y and multiply the inverse of r of x. And r of x was e to the x to the 3, so then what we get here is going to be negative e to the negative x to the 3 cosine of x plus e to the negative x to the 3 times the constant. Some of you will be tempted to label this as a constant. Some of you guys might label this entire thing as c, like let the constant absorb that. But you can't do that because what you have here is not a constant. It's a function. So you leave it as is. This is your final